it's not it's not the worst yet. I'm just going to do the announcement for the talking break today. Okay, can everyone hear me? Okay, good. So we are going to start today's seminar by Max Häberle. Is it correct, the pronunciation, more or less? But before starting, I just want to make two short announcements. The first one, the coffee breaks are back to the seminar, so at 11:30 we can meet in the cafeteria to share a coffee together. And second point, if the PhD student in the room and in the Zoom can either come to the desk at the end or send a message to Tanya, because we don't have the Zoom account seminarios anymore, just so I can check their presence, because I don't know all the names. So now if you want to introduce here.
Good morning, everyone. It's a pleasure to introduce Maximilian Häberle, or Max, from ISO Garching. So he did his PhD at Max Planck Institute for Astronomy in Heidelberg. So we spent some time together, the same time there. He did a PhD combined with science and instrumentation. So his supervisors were Nadine Neumeier and Tom Erbs for the two parts, science and instrumentation. And actually his PhD thesis was about Omega Centauri and the local volume mapper. And Max is here these days and then next week for the local volume mapper meeting. So yeah, feel free to speak to him if you want. So yes, let's start.
Yeah, thank you very much, Francesca, for the introduction and also for hosting me here at IAC. It's a pleasure to be here. I'm also looking forward to the conference next week. And so I want to talk a little bit about my work on Omega Centauri, and then in the end focusing on the intermediate mass black hole candidate that we have found in the center. The talk is split into 4 different parts. I will start with a general introduction about Omega Centauri. Then I want to present you the oMEGACat project in which we study Omega Centauri. And I will give an overview of the different science topics that we are tackling and also about the data that we have collected for this project. And then finally, I will focus on one science case, which is the intermediate mass black hole in the center of Omega Cent. And I will end my talk with the plans that we have on the future and the follow-up observations that we are conducting at the moment. So starting with Omega Centauri, I have a small quiz. Can you spot Omega Centauri in this white field picture of the Milky Way? You can check whether you were right. It is up here, located above the galactic plane. And I think actually from here, you're already south enough that you can see it. Must reach about 20 degrees over the horizon. But it's a southern target. But indeed, it's an object that can be observed with the bare eye. It's actually the most or the brightest globular cluster that we can observe from Earth. It's also the most massive globular cluster of the Milky Way. So if you do some dynamical models, you can estimate its present day mass to be about 4 million solar masses, and that it means it contains probably above 10 million stars. It's located in the Milky Way halo on a retrograde orbit, and it's relatively close to us. So its distance is about 5.5 kiloparsec, and that means that we can study it in great detail. And so people have been looking at this cluster since many decades, and it turned out that it is actually different than other globular clusters that we can observe in the Milky Way. And the differences are that Omega Centauri shows very complex stellar populations with both the spread in age and in metallicity. And so it's nowadays quite well known that most globular clusters seem to host multiple stellar populations, but the differences in these stellar populations of your more typical globular cluster are just in light elements, while the The stars in Omega Centauri show a wide spread, for example, also in iron abundance of more than one dex. And another way to study this, besides spectroscopic metallicity studies, is to look at precise color magnitude diagrams, especially in the blue and ultraviolet. And this has been done very successfully with the Hubble Space Telescope. You can see here in the right plot a UV color magnitude diagram. And you can see that there are multiple split sequences. You can see multiple turn-off points, and this is due to the complex stellar populations in Omega Centauri. And this has led to the scenario that Omega Centauri is likely the stripped nucleus of an accreted dwarf galaxy. To explain a bit better what we mean by this is, I will take one step back and talk a bit about the accretion history of the Milky Way. So the accretion history of the Milky Way is a very hot topic at the moment, because with large surveys such as Gaia, but also large spectroscopic surveys, we can now really disentangle how the Milky Way has formed. And we have found many streams and remainders of past accretion events in which the Milky Way has accreted smaller dwarf galaxies, and then typically these dwarf galaxies get disrupted. Their stars get scattered around the halo of the Milky Way, and we need, for example, spectroscopic or kinematic signatures to trace them back. Here you can see an illustration on the right of how the stars are distributed. And the most prominent example is probably the Gaia Enceladus sausage structure, which was believed to have merged with the Milky Way around 10 billion years ago. And while the stellar component of these dwarf galaxies gets scattered around the halo of the Milky Way, both the globular clusters and the dense nuclear star clusters of the accreted dwarf galaxy are sufficiently bound that they can survive this accretion event, and then they remain in the halo of the Milky Way. So we believe that Omega Centauri is likely the remaining nucleus of such an accreted dwarf galaxy, both because of its high mass, its complex stellar populations, but also its overall kinematics, for example, that it's on this retrograde orbit. And it has been suggested that it actually may even be the nucleus of the Gaia Enceladus galaxy or the Sequoia progenitor, but this is still ongoing investigations. And this makes Omega Centauri something very special, because it's very close to us. So it would be the nearest nuclear star cluster, even closer than the galactic center of the Milky Way. It's also the example of the core region of a dwarf galaxy whose evolution got halted when it got stripped of all of its gas many billion years ago. And it's also a witness to a major merger of the Milky Way. And for this reason, Nadine Neumeier, who was my PhD supervisor, and Anil Sess, who is another close collaborator, have initiated the oMEGACat project, in which we aim to understand both the formation history, but also the present-day properties of Omega Centauri. So this brings me to the second part of my talk, in which I want to present this project to you. Again, the goal is to understand both the formation history and the present-day dynamics of Omega Centauri. And to do that, we have actually collected the largest data set ever assembled for a globular cluster. We have created a spectroscopic catalog for more than 300,000 stars. And I have created a proper motion and multi-band photometry catalog for around 1.5 million stars. Talk a little bit more about the details of these catalogs in a bit. But these catalogs are fully public since about 2 years. So if you want to do your own investigations, we are very happy to support that. And you can use our project website to access them. The spectroscopic part of the data was observed using a large mosaic with the VLT Muse integral field spectrograph. We cover the region out to about the half-light radius of the cluster, which is 5 arc-minutes, and marked with the green circle in the plot on the right. And you can see that one needs slightly above 100 pointings to cover this large area. So this was quite a big effort, and my fellow PhD student Selina Nichai then has extracted spectra for more than 300,000 stars in that region. And then from these spectra, we can measure line-of-sight velocities and metallicities for individual stars. Then the second component of the catalog is based on Hubble Space Telescope imaging. And to do that, we have used both large amounts of archival data that was available. We have also added our own new observations. I'll talk a bit about the reasons on the next slide. And then I have done a state-of-the-art astrometric reduction to measure proper motions using these HST observations, but also photometry in multiple filters. And I have prepared a small animation. Let's see whether I can see it here. Oh, yeah, it started, sorry. I'm too quick. Okay, so here I show all the observations of the Hubble Space Telescope that were taken for Omega Centauri. So we're taken with two different instruments, ACS Wide Field Camera and Wide Field Camera 3. You can see that observations started already back in 2002. That's when this large mosaic was done. And then you can see that we have a very large number of observations focusing the center of Omega Centauri. And you might ask yourself, why are they going back so often to this field? But the reason is actually that the center of Omega Centauri is the calibration field for the UVIS camera. So for us, that was, of course, a really lucky situation. And you can see that we added a ring of additional observations. This is to have a second epoch and to be able to measure proper motions. Now you can see how we zoom into the center of Omega Centauri. You can appreciate the resolution and the depth of the HST images. And you can also see all stages of stellar evolution, so red giants, blue horizontal branch stars, lots of main sequence stars, and now you also see some white dwarfs popping up as the pale blue dots in this image. So at the end of this large data analysis, which took about 3 years to complete, we have created a proper motion catalog with 1.4 million stars within the half-light radius. It has a uniform long temporal baseline. So the first observations were from 2002, and now the last epoch was from 2023. And so therefore we have more than 20 years to track the motion of the stars. In the very center, we have up to 450 individual measurements, and we reach quite a faint depth. And the median error on the proper motions for bright stars is just 6.6 micro arc seconds per year, which at the distance of Omega Centauri translates to just 0.2 kilometers per second. So we can really start to see the motion of the individual stars. One way to visualize this is to look at a so-called vector point diagram. This is what you see here on the left. A vector point diagram shows the two proper motion components, so right ascension and declination, plotted against each other. And you can see that there's this almost perfectly circular cloud of points at the origin. Those are the member stars of Omega Centauri. And you can actually also see here that we have measured our proper motions relative to the bulk motion of Omega Centauri. That's why it's centered here at the origin. But then you also see other overdensities here. So for example, here, this cloud, those are likely foreground stars. And then towards the left, we start to see background sources and background galaxies. And then on the right, you see the same sample, but this time plotted in the color magnitude diagram to also show the photometric component of the catalog. And then if you make a simple selection here on the left, you can see that the stars that have a proper motion that is large or with respect to the center of Omega Centauri show a very different structure in the color magnitude diagram. The combined catalogs, so the photometry, astrometry, and spectroscopy, have been now used for quite a few different science projects. I have a long list here. We are publishing them as a series, but the science cases are quite broad. So we study the dynamics, but we also study the formation history, the chemistry of the multiple populations. We have a paper where we study where we search for the intercluster medium in Omega Centauri. And I will just present a handful of different highlights. So one of them is here. You can see a magnitude diagram on the left, but this time it's color-coded by the metallicity of the stars, because we have measured the metallicities with Muse for all these bright stars. And you can see that the different sequences that we see here in the color magnitude diagram along the red giant branch, they also show very different metallicities. So it's a nice way of understanding this. And then I don't know how deep you are into multiple stellar population studies of globular clusters, but one way of disentangling them is to create these pseudo color diagrams that are called chromosome maps by some authors. So basically, it's a special rectified color plot, and all the different populations land in different spots. So this is what you see here on the right. And again, we can attribute different metallicities to these different locations in the chromosome map. But now we are actually also trying to measure other elemental abundances. Then another very nice science application has been the study of the age metallicity relation of Omega Centauri. And to do that, my colleague Kali Klons, who's still at MPIA, created very refined isochrones matched to Omega Centauri's properties, and then fit the ages of stars in the sub-giant branch region. And then we could use our metallicity measurements to create an age metallicity relation for 8,000 stars. And this actually shows quite a few interesting properties. So you see here the age metallicity region on the right. And you can see that there's at least two different sequences or groups of stars here. So we have this relatively narrow sequence here, which in the end looks a bit like self-enrichment. And then there's this more diffuse component at higher metallicities. And we are still trying to find a scenario that explains these observations. Then another thing that we can do is that we can study the kinematics of Omega Centauri in 3 dimensions, because for tens of thousands of stars, we have basically the full 3D velocity vector. And so here on the left, you see a map of the velocity dispersion as measured with the Hubble proper motions. You can see that we can do this in a very fine grid, in a very precise way. And then we can also look at the line of sight velocities. And in the line of sight velocities, we see a clear rotation pattern. This is what is shown here. We also can determine the velocity dispersion in the line of sight velocities. And then if we combine that, we can also measure the dynamical distance to Omega Centauri. Okay, then the last science case I want to focus on a bit more closely is the intermediate mass black hole candidate in the center of Omega Centauri. And before we start with that, I give a brief introduction to intermediate mass black holes in general. So black holes have been observed mainly in 2 different disjunct mass ranges. On the low mass end, we have stellar mass black holes, which are observed as X-ray binaries, or recently the famous Gaia black holes, or also gravitational wave binary black hole mergers. But they reach masses of up to 100 or 150 solar masses, and are believed to be the endpoints of stellar evolution of massive stars. And then on the other end of the mass range, we have supermassive black holes, which reside in the centers of most galaxies. and weighed at least 100,000 solar masses. But then, of course, there's also supermassive black holes that can reach multiple billions of solar masses. And then there's this relatively large mass range from 100 to 100,000 solar masses, in which we have only very few candidates. And this is the so-called intermediate mass black hole range. And it would be very interesting to know more about these intermediate mass black holes, because this could help us to better understand also the supermassive black hole formation in the early universe. So when looking at distant quasars or recent JWST observations, we can see that supermassive black holes seem to have formed at very high redshifts in the very early universe. But how they exactly formed is still unclear, and there's different seeding mechanisms. All of them involve some smaller black holes. And if we could find or study the local intermediate mass black hole population, we could discern between the different seeding scenarios. Now, maybe one of the most promising locations to search for intermediate mass black holes are the centers of dense star clusters, because this is where they could form. And Omega Centauri, as the most massive globular cluster of the Milky Way, has been targeted to intermediate mass black hole searches since quite some time. So the first claimed detections were by Eva Noyola in 2008, where they found, using dynamical models, evidence for an intermediate mass black hole with a mass of around 40,000 solar masses. But then there were also quite a few papers that disputed these results for various different reasons. And in general, it has been very difficult to establish the presence of an intermediate mass black hole in Omega Centauri. First, because Omega Centauri has such an extended flat core, so it's not really easy to determine its center. And it might be that the first observations actually might just have missed the center by 10 arc seconds or so. Then there's the potential mass contribution of a cluster of stellar mass black holes that may mimic the kinematic influence of an intermediate mass black hole. This is also what Andres has proposed in his paper from 2024. And then another reason is that if we have a black hole in a dense star cluster such as Omega Centauri, we would expect that there are at least a few stars in the vicinity of the black hole, and they would then move much faster than the other stars in the star cluster. But there have been quite a few searches for these fast-moving stars, but they have not been discovered yet. And then finally, also no accretion has been found, neither in deep X-ray studies nor in the radio. And so we have now created this very deep, very precise proper motion catalog. So one of the first questions that we ask, can we find the fast stars that are predicted in case there's an intermediate mass black hole? And so to do that, right after the determination of the proper motion had finished, I looked at this 40 by 40 arc second region in the center of Omega Centauri. And the reason I chose this large region was that it encompasses all the different centers that were proposed in the literature. So I looked at the velocity distribution of the stars in the inner 20 arc seconds. And
starts with that proper motions, dollars. And probably you have also figured out because to avoid
okay, that's the question. Because it's for the people online to hear, and we give you the microphone and you know the talk, and you can talk about this. I'm sorry.
So I can quickly repeat the question. The question is whether we have filtered out stars with large proper motions by our method. So we have not done that. We have determined the proper motions with respect to the bulk motion of the cluster, but we do have measurements for stars with high proper motions. And in this plot that I have shown with the circular selection, that was just to demonstrate the effect of this proper motion selection, but we have not applied that selection to the search that I present now. Actually, we have done the opposite thing. We have made a selection in color magnitude space to restrict ourselves to likely cluster member stars. And then we looked at their proper motions. And so here you see the proper motion or the 2D velocity distribution of stars in this region in the inner most 20 arc seconds of Omega Centauri. You can see that there's this component which corresponds to a 2D Boltzmann distribution. Then we draw this line here, which is the escape velocity as predicted by dynamical models. And this is should be around 62 kilometers per second. And indeed, we saw some stars that seem to have moved faster than the escape velocity. So the question is, where are these stars located? And there we found something really interesting because we found some stars scattered around, which might be foreground sources. But then we found this very strong concentration of fast-moving stars in the innermost few arc seconds of the globular cluster. So zooming in more, we found 7 stars moving faster than the escape velocity close to the photometric cluster center. And actually 4 of them were even within 1 arc second. And all of these fast-moving stars lie on the cluster main sequence, as you can see here in the color magnitude diagram towards the right. The 4 fastest moving stars lay within 1 arc second. And curiously, the centermost star was also the fastest, with a velocity of 113 kilometers per second, which is almost twice as high as the cluster escape velocity. And so this got us very excited, of course, but then we also had to check both the data quality for these measurements and some other scenarios. I'll show you a few of these tests on the next slides. So here you can see the raw astrometry for the fastest moving star in the sample. And you can see here the great advantage of the HST data set that we had available, where we have these hundreds of observations tracking the position of the stars over the year. And 130 kilometers per second translates to about 2 HST pixels in 20 years, which does not sound like a lot, but actually that's something that we can measure very easily. And it's something that you can actually spot with your bare eyes. So you can see here the position of the star in 2002. You can see that as the years pass by, it moves towards the upper left in the small region that is shown here. Then another scenario that we tested that we have for our background Milky Way stars, because as you have seen in this vector point diagram, these stars have a large proper motion with respect to Omega Centauri. And to test this alternative scenario, we looked at the density of fast-moving stars at large radii, where we would expect them to be fully foreground. And we also looked at the theoretical model of the Milky Way, a Bersasson model, and we found a very consistent low foreground fraction using both methods. And so in the 3 arc second region in which we have observed the 7 fast-moving stars, we would just expect 0.1 stars from the foreground, and then we can just do some simple statistics to rule out that this is pure coincidence. I think the next point that we had to check was one of the more important ones. This could be that we have assumed a wrong value for the escape velocity, because in the end the escape velocity comes from dynamical models and they have a few uncertainties, but can actually also confirm the escape velocity empirically. So here you see again the 2D velocity distributions for the stars in the center of Omega Centauri. Here on the left you see the inner 3 arc seconds where you have the fast moving stars. Then if we go out to slightly larger radii, so a region from 3 to 10 arc seconds, we can see here that the velocity distribution basically cuts off exactly at the assumed escape velocity value, with one exception. And so we think the 62 kilometers per second are actually quite an accurate value. Then it could be that these stars are moving fast because they are in tight binaries with a dark companion, for example, a stellar mass black hole. But again, there the long baseline that we have is an advantage, because if we would have such binaries, then we would have observed basically the full curved orbit already. But the stars seem to move in straight lines and over the time that we have observed them. Then it could also be that these stars are accelerated by binary interactions and are actually unbound from the cluster and are on their way out. But this would not explain their strong concentration towards the center, because you would expect these interactions to also happen elsewhere in the cluster. And also then the number would be unsustainably large, because we would have to eject a star every 100 years or so, and then deplete Omega Centauri of all stars rather quickly. And so we think the most likely scenario for the stars is that they are indeed bound to an intermediate mass black hole. But then the question is, of course, what can we learn about that intermediate mass black hole candidate? And quite a few parameters are still unknown to us. We do not know the exact position of the intermediate mass black hole. We do not know the line of sight distances to these stars. And we also do not know their velocities, because they were too faint for our MUSE observations. What we still can do is calculate the minimum mass that is needed to keep all these stars bound. And this is, I think, illustrated well in this plot here on the right, which is an escape velocity profile for different scenarios. So if we do not have an intermediate mass black hole, then this escape velocity would be rather flat in the inner 100 arc seconds or so of the cluster, because it's dominated by the stellar mass outside of the center. But then if we add an intermediate mass black hole of 8,200 solar masses, then this is just enough to keep all the fast moving stars bound. And so this is the lower limit that we can derive. And then if we assume an even higher mass, for example, the 40,000 solar masses that have been proposed in the literature, then this would comfortably fit all the fast moving stars and keep them bound. And the reality is probably somewhere between, I would guess, because in the end, the stellar velocities are slightly higher, because we are missing the third component. And also the distances in reality are a little bit higher, because we are also missing the 3D component of the line of sight distance. And so yeah, this places the black hole right in the middle of the intermediate mass black hole range. And it's also a result that is relatively independent of dynamical modeling, because it's based on these direct observations of the individual fast stars. And now, of course, we do want to learn the exact mass of the black hole and want to study this further. And so we have started quite a few follow-up programs that I want to present now in the last bit of my talk. So there's, I would say, two lines of evidence one can follow. One would be to search for accretion signals, which is somehow completely independent of the stellar kinematics that we have observed. And indeed, there have been quite a few different programs. One is based on JWST observations and actually has been proposed already for cycle 2, so independent of our results here. And then we have proposed for some deep ALMA observations. The other line of evidence is to improve our constraints on the stellar kinematics in the center. And so we can do deep integral field unit studies to also measure the line of sight velocities of these faint stars. And finally, we can continue the astrometric monitoring of these fast-moving stars with the ultimate goal to maybe measure astrometric accelerations or find additional stars that were too faint for the existing observations. So I quickly summarize where we are with these different programs. So there's this Cycle 2 program led by Oleg Kagaltsev and Stephen Chen using mid-infrared James Webb observations. Their results have been recently on arXiv, and they have found no detection. Also, it seems like radio follow-up actually shows no detection. And the challenge here is that we actually know very little about the gas fraction in the center of Omega Centauri, but it's likely very low. So therefore, all accretion signals that we would expect are also very weak. Also don't know much about the accretion mechanisms in these very low accretion Eddington regimes. Then we have recently conducted IFU observations of the center of Omega Centauri with a near-spec IFU. There's basically two instruments with one can measure the line of sight velocities for these stars. One would be MUSE in narrow field mode. I've been trying now for a few cycles to get these observations, but one needs a lot of time because these stars are faint. But we had more luck with near-spec. So we have very deep observations with about 20 hours exposure time. The challenge with near-spec is that the spatial resolution is not great. So the specs are 100 milliarcseconds. And you can see here actually the collapsed cube of the data here. You can see all the stars. The green stars here are the known fast-moving stars. And one has to be very careful with subtracting the neighbors and so on. So the data reduction is ongoing. But after some initial challenges, it looks quite promising now. Then the final program I want to present is astrometric monitoring of the fast stars. Because if we can measure accelerations, then this would provide a direct mass measurement of the intermediate mass black hole, similar to what is done in the galactic center with the famous S stars. And actually, the spatial scales that we have in Omega Centauri and with the fast-moving stars are quite similar to what we have in the galactic center. So this is illustrated here in the plot on the right, which is in physical units. And the gray stars are the known S stars in the galactic center. The pink markers are the stars that we have in Omega Centauri. But the difference is, of course, that the black hole in the center of the Milky Way is likely a factor of 100 more massive than the black hole in Omega Centauri. That's why the time scales in Omega Centauri are much, much longer. And so if the S2 star in the galactic center takes 17 years to orbit its black hole, then it would take at least 170 years in Omega Centauri. So that will take a while. But what we can do is we can extend the time scales of the existing observations, and we can push for better precision because, of course, you do not need to observe the full orbit to make an acceleration measurement. This is why we have started a NIRCam monitoring campaign. And I will give you a brief preview of that data. So here you see this image is our HST image, which covers more or less the half-light region. These are the new JWST observations that we have added. There is NIRCam, which has this rectangular footprint, and we have actually also taken a parallel observation with the NIRS instrument to study the outskirts of Omega Centauri as well. Here you see a comparison between the HST observations in the F814 filter, so also I-band. And here you see JWST NIRCam F115. So the wavelengths are rather comparable. And if you look at a rather large field of view, like here, 1 by 1 arc minute, then the images actually look rather similar. You can, of course, see the characteristic PSF of JWST on the right. But then if we zoom in further, then we can see that actually the spatial resolution of JWST is significantly better than what we had with HST. And also the sensitivity is much higher because of the much bigger mirror, of course. So maybe to illustrate that better, I start here blinking between the two images. You can see how the James Webb image is sharper. And another very nice thing is because in these images we now have about 13 years baseline, and that is actually enough to see the fast moving stars by eye. So here you see the fastest one jumping around, but there's another one here and another one here. And so this is, at the moment, this is a nice confirmation of the HST only findings, but then with future cycles, we were able to place stronger constraints on the accelerations. So this is a preliminary analysis here of the new data. So you can see in black here the HST data. You can see the observations of JWST here on the right. What you can notice is that the scatter is much, much lower. And the reason is the better spatial resolution, but actually the resolution is better by a factor of 1.5 or 2 or so. What makes a larger difference for these faint stars is that the signal to noise of our measurements is much, much higher. And so we think that in the next 3 years or so, we can add new constraints. Whether we detect accelerations depends a bit where exactly the black hole is and how massive it is. But if we cannot do it with these JWST observations, then we actually might be able to do it with the future extremely large telescope, because then this yields another significant jump in spatial resolution. And I think the instrument that is best suited for this will be ELT Mikado. So we are eagerly waiting for that, but the James Webb observations can bridge the gap. And then at the same time, we are also pushing to update the dynamical models of Omega Centauri. So we are creating new dynamical models for better mass constraints, but also N-body models with a higher number of particles, and including both stellar mass black holes and an intermediate mass black hole. And so to summarize my talk in a few main points, Omega Centauri is a unique probe for low mass galactic nuclei, making it a very valuable laboratory for us. In the oMEGACat project, we have created a very large data set having astrometry, photometry, and spectroscopy. And then this allows us to study the formation history of Omega Centauri, its stellar populations, and its kinematics. And using these new catalogs, we have found 7 fast-moving stars in the center that provide a lower limit of 8,200 solar masses for an intermediate mass black hole in Omega Centauri. And before I end now, I just want also to invite all students or postdocs that are curious about working at ESO to get in touch with me. I'm happy to help you or assist you or answer your questions. Thank you.
Okay, thanks for the very interesting presentation. Do we have some questions in the room or in the Zoom? You can also activate your mic to ask some questions.
So fantastic talk, fantastic work as well. And I mean, I have like 2 questions. One had to, I mean, it's something very naive, but would you expect some sort of lensing effect of some of the stars of the Omega Centauri by the black hole, so that you see an increase of brightness of the star, not just the motion? Have you thought about that? And the second is about the kinematic. I mean, you have detected 7 stars with large proper motion, but I think that it should perturb the whole set of stars that are nearby. So it will produce something else in addition to these stars. How big is this effect, and are you thinking of studying that, or?
Okay, thanks for these questions about the lensing. So I think for the intermediate mass black hole to lens, we would have to be very lucky that we have just the right geometrical.
You have so many stars in Omega Centauri that maybe by chance.
what we are actually indeed trying is to search for stellar mass black holes this way, because we have this very long time series of observations. And so what we are looking at is whether we can detect a microlensing event in which an individual star gets brighter for a while it's lensed by a stellar mass black hole, and then gets fainter again. So we are at the moment digging through the photometric time series to find events like that. I think in principle, if we are lucky, there could also be a star where this happens for the IMBH, but I think it actually would be quite a coincidence. And then the second question is, let me quickly see whether I have a slide for that. Maybe I go back here. So what actually people have done in the past is to look at the velocity dispersion in general for all stars. We have also done that with the new data, and actually indeed you can see that the region that is here closest to the center shows the highest velocity dispersion. So one can include this in dynamical models, and then also try to constrain the intermediate mass black hole that way. The challenge is that Omega Centauri has a very flat density profile in its core. And so that means that if you look at the center of Omega Centauri, many stars are just close to the center in projection, while the actual number being physically close to the black hole is much, much lower. So we are actually trying to model it also this way. And it looks like with a black hole of 20 or 30,000 solar masses, we would expect the found number of fast-moving stars in the immediate vicinity of the black hole. But then again, it's not very easy because it very sensitively depends on the slope of the number density profile in the center.
Thank you.
Yeah. So in fact, I wanted to ask you about did you, I mean, for those stars, these 7 stars, right? So do you know the metallicity for those, in particular, those stars? That's a first question. Okay, so maybe we can.
Not yet. So they are too faint to be included in our spectroscopic sample. Let's see, maybe we can do something with the JWST spectra.
I see. That would be very important indeed. No. Now you mentioned, and in fact, I'm not sure whether I think you didn't show like this the velocity dispersion profile of that region.
Yeah, here's a 2D map, but
yeah, but so you said that it's not let's say not according to expectation to be like more peaky than where I mean, around the black hole.
So again, this relates to the fact that we are looking at the cluster in projection, and so we see the velocity dispersion is dominated by the larger number of stars that are not physically close to the black hole.
Yeah. Okay. Now changing now. I mean, as you know, I mean, this cluster is one, if not the most, with the highest fraction of extreme horizontal branch. Okay, is already has been reached a consensus on why, and this is the case, no? And you showed a plot, in fact, about the
I call a magnitude diagram.
the HR diagram. Okay, so maybe you can get there to. Yeah. So you can see how extended
many of them, yes.
The horizontal branch. So, but this is mostly at low metallicity. I mean, it's important to, I mean, I find it like important to show what the metallicity is that
Mhm.
you wanted to
Mhm.
tell. Because it's an extreme horizontal branch
Mhm.
due to high metallicity or due to the typical horizontal branch morphology
Mhm.
that you would expect on metal poor.
Yeah, I
So
think
this is
that's an interesting point, and I have to admit that we have actually excluded the horizontal branch stars and the blue stragglers for this first analysis because in the end they show very different spectra, so they need tailored solutions to reliably determine their metallicity. There's one collaborator in our collaboration, Marilyn Latour, who has more expertise on hot stars, and she's trying to use the combined HST photometry and the Muse spectra to learn more about the horizontal branch stars in Omega Centauri.
that would be very interesting, in fact,
Yes.
to distinguish among the scenarios that have been proposed for this extreme horizontal branch. Let's say it's one of the, if not the most, okay, that having this highest fraction. So,
Yeah.
thanks.
Yeah.
Thanks for the beautiful talk and the work. It's impressive. Just a curiosity, how does it work with the JWST program that you have with NIRCam, I think it is?
Mhm.
Is it like on for several cycles? And how many cycles do you think you need to measure the acceleration accurately?
So the program was approved for 3 cycles. That's the current maximum for multi-cycle programs. And in addition, there's this one cycle 2 observation by the other program that was looking for accretion. So going back to this plot, you can see that there are already 2 JWST epochs now. So there's this one from cycle 2, was observed in 2024, and then there's this one from last summer, 2025, and we will add 2 more data points. I will push for them being spaced 2 years because then that gives us stronger constraints. Whether this will be enough is unclear. So we have simulated that we can decrease the acceleration error or the upper limit on accelerations by a factor of 2 with these new JWST observations. And maybe that's enough. Maybe we need longer baselines. So then in 2 years, I will be proposing for an extension.
Okay, do we have other questions in the room?
So I was just wondering, can you explain why the fast-moving stars are so faint?
That's another interesting thing. I mean, faint stars are quite numerous, and it's borderline statistically significant. So I've run some Monte Carlo simulations to see whether this could just be a coincidence, and I think the chance for it being pure coincidence is about 2%. So the hope is that maybe with JWST we can push for more fainter stars, and then we can test whether this is just a random coincidence or whether it's a true effect. But then on the other hand, it looks like with JWST we are now reaching somehow the end of the luminosity function, so the number of stars that we can add is not too high. Let's see, maybe we get
Okay,
a
thanks.
few more stars.
Do we have other questions or online? No. Okay. We have to fill 5 minutes before the coffee break, so more questions, please.
Thank you. Very interesting talk. My question was more like the number of the fast stars that you found, and maybe like finding more with the new campaigns of the GWST, and also like one question: if like
you would expect to like find more of those, and maybe a number, probably difficult thing to say. But other was when you show the minimum mass constraint of the intermediate mass black hole, and the other one of the 40,000 solar masses. If maybe naive question, if that would be the case of such high mass, would not you expect to have already more fast moving stars? That is.
I think those are two very good points. So we do expect to detect additional fast-moving stars with the new observations. On the one hand, with the line of sight observations, because there might be a star that is moving, let's say, with 60 kilometers per second in 2D, but then you add the third dimension and you see that it's actually moving a little bit faster. And then if there are stars that were too faint to be observed with HST, then we might detect them in the new JWST campaigns. Actual numbers will be, I think, lower than the number than what we already have. So maybe if we are lucky, we get 5. If we are not so lucky, we get 3, something like that. I was already looking at this image very long to see whether there might be something that we have missed in the present catalog. For example, here you see that there's something moving relatively fast, but with the additional JWST epochs, we then can clarify whether this is a real high proper motion star. And then the second question.
The second question was about if the mass constraint of the black hole would be more to higher masses. Already in the plot that you showed, seemed like maybe.
So this is something we are trying to model basically the black hole mass based on the number of detectable fast-moving stars, and at the moment it looks like we get a best fit mass with the existing number between 20 and 30,000 solar masses. But again, it depends quite sensitively on the number density profile that you assume, because if the number density profile steepens towards the center and you have more stars close to the black hole, then you would expect a higher number, and vice versa. And then if we add more stars to the sample, then this could work even better.
Okay, thank you.
Okay, so many colleagues told me that actually it's time for the coffee break. So let's thank our speaker again, and we can go after to continue the discussion in the cafeteria.